welcome to my talk. With the word, it's Rhizome. It's one of my favorite words I learned 30 years before in university. As you might not know, I'm not a computer scientist, but psychology and philosophy, and there it is a very good term, and I like the word. But it only expresses my fascination of interconnected things, networks and such. So it's like the compose Kubernetes things that drive me, so the communication aspect. I mean, in Smalltalk we know the messaging is the main part of the whole system. It's not objects, actually. And from the network perspective, we all know the network is the computer. So this talk is a bit more like a hate-love relationship topic, because I'm forced to work at the LAPD for some time, which is the least annoying persistence department. Because after 30 years, for me, it's most of the database solutions, I just can't get it. So I won't. And so I will tell a little bit of my annoying past, what we achieved so far, and of the goals I'm trying to achieve. Well, it's not there yet. I collected all the pieces, which I will present, but it's not there yet, I hope. Maybe next year I can present that. So why I'm doing this is because some of you might know, I presented already, is ActiveGrid. It's a web-based application for digital business processes. And kind of it is making your database schema. So you click like Excel, but columns have types, and you build a database structure while clicking on the web. So it's highly dynamic. And we have a database, a workflow system, and a wiki, or a web presentation layer, and we want all the objects to be interconnected as possible. So, and now we're getting into the persistence topic, is that most databases don't allow really these highly interconnected or polymorph approach to an application. So, but for a project, you usually would start saying take any database. So which is the database that has the most deployments on this planet? Any ideas? Exactly. So some of you might have thought about Postgres, but if you look at your mobile phone and everywhere, it has SQLite. So it exceeds the deployments of Postgres easily. All right, so we have SQLite. So what's the good part about SQLite? I mean, the one that some I talked in Smalltalks last year is like, I prefer databases to be libraries. So because I think that most performance characteristics are assets of architecture and not of components. So when a library usually gives you the freedom to choose your own architecture and adapt to it. What's the bad part about SQLite? It's the SQL. Actually. So yeah, it's easy to rip on something like SQL, but is SQL bad? Not at all. SQL is pretty awesome, just not for the purpose I'm trying to use it, because entities are not objects. So there is on the left side, we have the world where we want to live in, the object world. We feel comfortable. But an SQL database is an entity relationship engine. And entities are not the same as objects. So we have these, you see the intersection, there is something called object relational mapping that tries to tell you could have both, but the intersection is not that big for a reason, because you sacrifice the object world in order to have the entities. There's many reasons why this is the case, but the most important is polymorphism, which is one of our main driver. It's just not possible in SQL database. There were people trying to convince me, but no. You can hack around with dynamic mapping tables, with sparse tables, whatever. It's a hack, it doesn't work good, and it's really ridiculous. And you have to sacrifice everything you usually like foreign key constraints and such. So it's just not working. So come to me if you have a different opinion. But for now, I keep it. That's the reason why I started to use to develop an object-oriented database in the hope to get rid of all these. I mean, I had a lot of SQL experience, but at one project I saw 70% of my time was database schema migration, and all the stuff you don't like to do because your problem usually is something else. So what's soil? Soil, if you have a big model, it doesn't have to be big, but you have a model graph, and usually I told in the last talk that when we start a project, we just use image persistence because you have a business problem to solve, yeah? So you try to make your source code, and you don't want to care about all these annoying things. So you start just saving the image, perfect. So the image save plus the singleton is a super database to start with. But it's not something you can operate in a production environment, because why? Because to save an image, it takes a lot of time because you always save the whole image. And the every object is then global, so concurrency is not supported in the image. So when you have something like to install on a web server, you need something which only stores the stuff you changed and only reads the stuff you want to read. So, and soil is a way of having all your models you cut. There's references like the internal, the blue ones, and then you define something like an external reference, or we call it standalone object. So, and the blue ones, these objects are arbitrary, full blocks apart. So clean blocks, I think we could do. So these are stored together. So if you go to disk, the blue ones stored together, and you saw the 1:5, the 1:12. That's database addresses. So the cluster is stored saying, so here's another object, but this has a database address, not a direct reference. And this way, we make it that you have small graphs, so it's a design issue. You can define that yourself. You can store little clusters, which goes pretty fast. And when you read that, you see the light gray things. At that database position, you get a proxy. If you step over, does not understand, you don't care about it actually when you read that, because the proxy then gets the next cluster from the database, and you can transparently go through all the model graph. So you have just, when you store it, you design which is a standalone object, but on reading, you don't care. Soil uses serialization, so you have to put the objects in byte arrays. So there's the generic case, we just use the class layout to decide how you store an object in an indexed object. It's just the instance variables contents. In a variable length content, you have just a collection store, so it's easy. And then there are special cases, which are actually quite much 40, I guess, where you want to have a more effective way of storing it, because storing a string in the generic case would store a collection for an object for each character, and that you don't want to have. So for string, you can just say, okay, I'm storing the byte array. So and that's what you do. You just shortcut the complex stuff for the specific things, date and time. So there is a lot of objects where you use specialized serialization. It's all there. So soil in its thing, it's an object-oriented database, which is only relying on file streams and a few system calls like fsync, which flushes data to disks. The serializer, I just told, is either layout or a specific, so you can even in your code, you can use special serialization for your domain model objects. It stores partition graphs as clusters with addressing inside the database, so it's all there, and for the purpose of having a lot of data, which we usually have a big dictionary or something, it supports binary search indexes, which is B-tree and skip list, which you have in any database. So because if you have 1 million entries and you search something, you need a supporting structure, and the binary search structure is there for you to get the performance. Yeah, so we did that. I mean, I think 2 years before we released the first version, but then database is somehow magic, and then people start complaining and saying, okay, it's a library. You can do small talk, but it's only storing objects on the local disk, on one disk. Saying, yeah, but it's not that bad. In ActiveGrid, we use NFS, a network file server, which shares the files. So I'm not sure how different that is to a normal architecture, but I say, okay, point taken. Let's look at your architecture, which is the old style three-tiered application, which is still prominent. You have a front end going over the internet, ending up in an application server, which does actually translating the HTTP request to a SQL query. So, but it has only the logic, and then everything goes to the database server. So that's the common way of setting up things. Oops. But when we look at that, I have friends, they have really successful businesses, and I was just asking, what kind of machine do you rent when you have that database? And the answer is always the same. The biggest one they get, they have. So because it's a single thing and you don't want to make that fail, so you just rent these multi-gigabyte, blah, 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 super machine to have your central store running on it. But if we look closely, if you have Postgres or something, resilience is actually pretty bad. Because if that goes down, you're offline. And there is almost no tool which makes an automatic transition. So there's someone saying, so switch the secondary to primary and then reconnect, which usually is not a big problem, but we would like to avoid that. Yeah? Well, I would like to avoid that. What strikes me even more is that there is plenty of disks doing almost nothing. So there is machines for the logic, and there is disks. Well, in the past they were turning. The modern thing, they don't have to turn. So, but yeah, they're still there and could be used. So that's also something we could improve. And finally, one of the worst thing is everything is going over the network. And the one thing is, if you have a lot of data and you want to have a subset, then you have to have either you make a lazy query and you transfer a lot of data over the network in order to maybe filter out the one you need and throw away the rest. Or you make really complicated SQL queries, and to be honest, that's one sort of code duplication, if we think about it. Yeah? So you have the main model logic, and then you make everything magically in a join. You make all these queries to have the best way to get only the set of data you want to process. So, and that's what's actually wrong, because we want to have I quote Dale in that thing, you want to have a program going to the data, returning something, and not the data going to the program and being selected. So all of that can be improved. So the goal, I mean, making the database was already kind of a brave or stupid decision. That's for you to decide, because we had this product to do. But now saying go from brave to insane and pretend while running a business, we can develop a distributed database, because that would solve all the assets I'm just marking on the red side. Was saying that would be perfect. So we could even win the three-tiered architecture next time. Well, I would be curious what the complaints then would be. But let's figure out, maybe next year. So the general approach is avoid central components. I know most of them, a lot of people try and most of them fail. If we utilize all disks, it can be something good economically. And horizontal scaling is usually good first for resilience. That means you have a lot of components. If a few goes down, you should not have a problem immediately. Yeah? And the second is performance, but that we don't have the problem yet. So sadly, so I would like to have that problem, but we're still working on it. All right, so soil exists, but everything I show now is just the pieces I collected in order to do it. So the point is, if you don't want to have the central storage component, then what you do, have your data on only one computer. If you don't want to have that, you enter the era of replication. So replication is actually copying the data from one computer to another to have 2 copies or 3 copies. So that's don't try to understand it yet. That it's one way saying, this is, for me, it's all I need to replicate. So let's show a few of the details of how soil works and any database works, because the acid criteria, especially the durable stuff, is that we have a transaction in soil, and while you're doing the changes, you write a transaction log, which is a low-level way of operations applied to the database. which are not transaction dependent. When you do a commit, you first write that transaction log to disk and call fsync, or comparable sync, to be sure that's on disk. So fsync returns when all the pages, everything has been swapped out to disk, and saying this is persistent, I'm not going to lose this. And then you do the same transaction log and apply this to the heap, to the actual your database, the data. And that's why it's probably easy for us to do the replication, because replicate is just another use case of this transaction log. And now we're looking at the code again. So the first is just to get a URL, which would you put on the target server. Self nodes will be all the other nodes I want to copy to. And the only thing I have to do, you see, the transaction log soil serialize is because the transaction log, yet again, is a bunch of objects. So we can use the soil serializer to make it a binary. Easy, it's a one method call away. And the rest is just having the IP address at hand and just do a put on that URL with that binary. That's basically, in the happy way. Yeah? The happy path would be just like this, and we tried and it works. So that works at least if n equals r. What's n? It's the number of machines you try to use in your stuff. R being the replication factor, meaning the number of copies you have. You have your replication factor of, so saying 1 would be a bit weak, because if the machine goes down, you don't have the data available. If you have the replication factor of 2, you have 1 additional copy, which saves you from a lot of pain, from not available data to losing data. There's always a question of people if you need a replication of 3. I'm a fan of having a third copy of that. So, but some say it's not necessary. But that's up to you. So, but if the number of machines is bigger than the replication factor we want to use, then we have to say, on which of these hosts do I find my data? That's like, so if you have a replication of a factor of 3 and you have 4 machines, well, the odds are 75% or something you hit the right machine, but you might want to know upfront. So, and I'm a fan because Marcos did the B-tree soil, and I did the skip list because I'm always for these more stupid and fancy algorithms for doing things. And I found a really good one, and that's called rendezvous hashing. So that's the stuff. So what can we do? So we built identifiers of data location. So the name of the host plus the ID I want to look up identifies the location of the data. When I have these, I just use preferably non-cryptographic hash to make a number out of it. Because hashes are numbers, they are sortable. So I'm sorting by hash, as you prefer, ascending or descending. And then I do a copy from 2 of the replication factor. And now I know that node 2 is the primary, node 1 is the secondary, and node 3 is the ternary node for where the data resides. And the good thing about rendezvous hashing is that most applications have, if you have something like distributed storage, you need, yet again, a central component managing the location of these data. But the rendezvous hashing, every machine or every Faro image or every Smalltalk image out there can independently calculate the location of these. So when that's saying goal achieved, so still not central components, still have something like discovery in an easy way that we can have in a distributed environment. But there's more. So we are only talking about, well, the machine is something like physically or virtual. In one case, it's physical because there's a database. So the one thing we had, where is the data? But of course, in a load balanced system, you want to have multiple images on one host. So just replicate and something might be a bit less. So you need something like a communication in between. So you have something like all of your machines, all of your Faro images should be the database, but then you have some management and communication going on. But how do you do this? So because usually would saying, okay, I just connect to all of these images and exchange my information. But if you imagine there is 100 images, then 100 images need to do 99 connections to talk to the others. That would be a bit much. And then if it's 1,000 nodes, so that's not going to work because it's just like, it's not going linear. It's pretty bad, actually, in this state. And if the image, we have primaries, secondaries, and tertiary nodes, so you also need some kind of hard beating because you want to know when the primary is down. Then you go to the secondary and get the video. So for all of that, you need some kind of collaboration among the images, and we know direct connections don't do it. What COVID showed us is that there is a peer-to-peer communication that is based on epidemic spread or dissemination, how we call it. It's, yeah, I will show it soon. It's something which avoids the M times N problematic, so that every image has to connect anything. It's capable of using a constant bandwidth, so that means that the gossip protocol is that, so the basic I'm showing right now how it's working. Every image makes an arbitrary call to 3 others every second. Yeah? So that means so that the general characteristic is with 100 nodes or 100 images, we have 300 connections, and with 1,000, we have 3,000, which goes just linearly. So, but the main point is that in most distributed databases, you have to reserve a special percentage for communication. It's not the data exchange, but just to keep the thing running. So Kubernetes and all of these, they just do a lot of that. So in order to make that a bit, because I did not assume for you know, can you see that? That's a gossip protocol simulator. And that's just because I'm not sure who of you knows about gossip protocols, but so here I can say I have 30 nodes, and for you that it doesn't go too fast, we just have 1 other connect per second. And now we see we choose a start node, and then we just let it run. And then you see, oh, wait again. I think it was more than 1. Wait. Yeah. So everyone connects that and learns about the others. So then there's two arbitrary to the others, 3, and that's the way how they exchange information. So it takes about, well, it's 10, it's 11. So if we make that every second, it would take 11 seconds, which is not too great, but for management level, it would be good. But if we, as I said, use 3 other nodes, so it starts 1 node starts just connecting, well, there's peer nodes. You connect them, and then you learn the first, and then the next one connects, and he learns about the others. Everyone, so you don't have the direct connection that every node knows about another node by connecting, but there's a seed node that learns about image number 1, and if image number 2 comes in, this one knows 2 and says, hey, there's also image number 1. So it's like this, you know, Christian said that Pete meant Susie is not going to school. It's like every node tells about the other nodes, and that's the dissemination. It's like the best dissemination is if you get coffee in a company and you meet with people, and then other people needs, you know, how the gossip works. And for the, if we take 3 nodes, you see that even for 30 nodes, it goes pretty quick that all nodes are covered with the information. So this is cycle number 4. So it would be 4 seconds, even for 30 nodes, to always be to synchronized state. So there is duplication of data in this communication model because some of the nodes receive the same message. The protocol, yeah, duplication, there's a kind, well, I don't only have 30 minutes, so there's a 3-way acknowledgement that they make to not make data already knows. So every data is versioned. And so you ask the other one, I know host up to version 5 do you have anything new? And they're saying, okay, for node number 1, I have version 4, so I give you the diff. So I can explain later. It's too less time. I'm sorry. Yeah. So, but it works like it's incremental, and you're not duplicating all the stuff, because at the end it's saying, I have node number 5, and it's saying, yeah, me too. Then there's no exchange. It's saying, I'm up to date. It's just a protocol, the difference to get up to date. So, yeah, 30 minutes is not a lot of time. I'm sorry. Okay, and there's too many slides, as always. So, and then the last piece that I'm saying, there will be no way for me doing that on the side with a company, just distributed databases, because there is, we have the fallacies of distributed computing, and that's what most people do not understand, is that neither the network is reliable nor anything. So making assumption in a distributed environment is pretty hard. So I'm saying, okay, usually we have a lot of tests in a Smalltalk code. I'm saying this gives me a short, ActiveGrid has in the main component 2,500 tests. So that gives me some confidence to change something and saying, okay, this might be good. But yeah, for distributed component, it's different. It's way different. And then further research revealed something which is called discrete event simulation, which is a way that you can define a hierarchical model of your environment, where every subcomponent is in a timeline arranged with it's a mathematical formalism, so it's proven. So what it does is to map every component on a single timeline. So the assumption is that you have a component does something and you have an estimation about the next event it will happen. And that maps all on a central timeline, making it possible to make a simulated distributed environment in a single thread in your code. So I will show now. So that we have, we need to, wait. I think it's a bit small, right? Better? Okay. So if we have that network, so we're just saying this is just to show you a bit. So this is a simple example. I have an echo server. For those who do not know this, it's just one of the first servers that ever existed. It's just you can connect it, you send it something, and it sends the same thing back. It's just like looking if the network is working. So, and we define a model which in the inspector looks a bit better. So the network is composed of a router. That means it finds hosts by IP address, and then there's hosts on the network. Each host has a server, which you can see here. It's on port 7001. And the resolver is the same as the router looks for the IP address to find a host. The resolver finds, based on the port name, it finds the program to talk to. That's a usual setup on the network. And if you execute that, you get the timeline in the inspector, which is executed on that stuff. So it's a bit cryptic because I just started to make it happen. But the first thing, just saying, well, server 1, I told the server 1 that it should here. That it's the first one to take action. It should just say hello to server number 2. And so you see there's an outgoing message from server number 1, then it reached the router, then the network, then it looked at the server number 2, it gets to the host number 2, the resolver looked at the port address and find the server. It's just like any network works. And then the echo server just saying, okay, I'm sending that back, hello, and then it goes the way back. The important thing is if you look at the second column, which is called time, that is what the framework and the formalism does. That with all the components, how they act, you construct a timeline, which is linear. And the additional thing you get is that the time in between two events can be skipped. Because kind of how the formalism works, it doesn't matter if it's 1 hour or something, we just can do it the next. So it's not waiting 1 hour, but if it is the next event, that will be triggered. So you will have a timeline, which is a kind of it goes forwards, and then it gives the signals, the events to the components so they react in a certain way. And even if it's simple, in the end, it should look like this, where you're saying, I have a unit test, I have my simulation, my network, and I do all of this, and then I have my assertions. And the purpose is saying, we have all these nodes, they communicate for step up to 5, and then there's a network error. Because you have a test case where you're saying, okay, they talk until this time, and then I check the network error. What will happen? Because the network is not reliable. And then you have a chance to see how the system connects, and then you put your assertion to saying, did you work properly in this distributed environment? So you can make a really complex setup and have simple unit tests to test it. Oh, well, already 1 minute over, but I have these. Yeah, so the discrete event system specification is a part. I found it on Squeaksource, and one of the students that did a PhD on this, we work on this together. It's called David Bashka, I don't know. It's, and yeah, that's it. Yeah. Yeah.
Thank you, Norbert. We have time for one question before the coffee break.
Yeah, because we said after this that there's a soil tutorial, maybe you can keep your questions even.
Or maybe we can do that.
So if it's really important, you can do now, but.
Well, okay, we have one question. So after there is also the tutorial, so you can ask more questions there.
Was it understandable?
Yes. You said you spent 70% of the time doing database migrations.
No, I did when I did SQL.
So how much time do you spend doing object migration in Soil?
Yeah, not at all. So
good.
So Soil has migration support. So what you do is you make a method with a pragma, saying this is for version 43, and then you get ended in a transaction, and then you can just saying user space do instance var cap blah blah copy, and that's it. We can discuss it later because I will be part of the Soil tutorial. So, which you should join, of course.
Thanks. Now we have the coffee.